5c, you're going to have a different issue. With 5c, you're looking at e to the t, e to the t, and you're going minus infinity less than t less than infinity, but here you're just going up. It's asking you to, yeah, I forgot to indicate direction, so this guy's going this way. This guy started at t equals 0 at the origin, goes up, hits this, comes back, and then goes back up. Okay. Now, with this, there, yeah, you're going to have an open circle at the origin. And you're still working along y equals x, but your parametrization looks like that. So why the open circle there at the origin?
Because it never actually reaches 0.
Yeah, e to the t has got a horizontal asymptote, but it's along the x-axis. E to the t is never 0, and it's also never negative, so you don't extend down this way. And the orientation is going this way because e to the t is an increasing function. Okay. T cubed, it's the same type of process. There shouldn't be troubles on that. Those circles should all be closed.
They had them open in the book too.
They did?
Yeah.
Yeah, they should be closed circles also there in 5D. I don't know why. I don't know where the goof is, but it's there.
Number 9.
9. Okay. So, fortunately, they're not asking you guys to graphing this, but they give you x equals t and y equals tan inverse of t cubed plus e to the t. So what they want you to know is basically what's the path. So I didn't make this analogy last time, but I should have. I usually do. When I write y equals x squared, it's like I'm looking at a map and I'm seeing a trail in the Smokies. It's like a path. But it's not telling me where I'm beginning and where I am at each point along the way. Okay. When I do a parametrized curve, I'm doing just that. I'm not only giving you the path that I'm walking, but I'm giving you what segment of the path and where I am at each individual time. So there is that distinction between the parametric curves and somebody writing out the formula that the curve is walking, the path that curve is walking on. So in problem 9, they ask you basically to get rid of time. Okay, and what's the path you're walking along? Well, if t is equal to x, I can just substitute in x every place I see a t. What I'm going to get here is y equals tan inverse of x cubed plus e to the x. Now, what that looks like, I don't know. I mean, I can tell you what tan inverse of t looks like, and probably this isn't all that different from tan inverse, but the rate at which it, tan inverse, if you had tan inverse of x, it looks like this. So I believe these are at pi over 2 and minus pi over 2. And my guess is all this does is hurry it along. But they're not asking you to sketch the graph. But probably if you look, the graph would be pretty similar to this. You'd see the differences probably if you superimpose. That would be my guess. Okay. But this is basically it for here. I'd have a little bit more trouble if they did something like x is t squared and y is tan inverse of t cubed plus e to the t. If it looked like this, I'd have to say t is equal to square root of x, except for when t is not square root of x, in which case it would be negative square root of x. And I'd have to give you different formulas depending on where I am. So this, it would be helpful if they said something like t is bigger than or equal to 0, because then I could use this formula. But if, once I have this, then I can write y is tan inverse of x to the 3/2 plus e to the square root of x. This would be when t is greater than or equal to 0, and this guy would get substituted in as well. Okay. So these sometimes can be hard to figure out. In all frankness, most of the time, if you randomly write these down or look at them, they're probably nasty to figure out, just like it is to graph very many of these. You basically need software to plot points. Plotting points is something pretty useless for humans, but the machines excel at that. They'll give you good pictures. Okay. However, we want to be able to do some relatively simple examples so we know what we're working with. 17? Yes. Okay, so 17, they give you x equals pi t, y is sine of t. So it's pretty similar to what I did here. And that is, I can solve this equation very easily for t. And once I have it for t, I can just take t and substitute in. So I can go x divided by pi is t, and then substitute that in and get y equals sine of x over pi. Since t is x over pi. And then as far as sketching the graph here, it's It's an issue of figuring out what the period is, and you're going to get a sine function of whatever period, and motion's going to go that way. Okay. So it's, you know, it's just algebraically manipulating, and keep in mind, all I have to do is write down something like this. And there's no way in the world that you're going to do it. You know, the point being, these typically are very difficult problems to do. And you can make these formulas, they don't even have to be this complicated. If I just wrote down two different fourth degree polynomials, you wouldn't be able to do these. So you have to say, well then why, what's the point? And the point is, say you've got some routine examples that you can look at, see what you can tell, what you can't tell, what you can do, what you can't. Okay? Way into the semester, we're going to be integrating on curves like this. You know, integrating around the curve. I mean, we have a lot of work to do to get there, but that's going to be where it's real helpful to be able to come up with parameterizations of some examples that are reasonably nice to get our hands on. Okay? Other questions?
I have a question about something we talked about last class. As for the vectors, okay, so you showed us two different ways to draw a vector, and we're adding v and w. And on the first one, it went from, like, you know, to draw the third part of the vector, it went from v to w, but the second one went from w to v, like the directional of it. And I was just wondering why.
Okay, let me, I was gonna go back through this anyways, so let me run on through. So, to get back to the stuff with vectors, I'm drawing a vector by indicating an arrow. The arrow is indicating the direction. The length of the vector corresponds to its magnitude. And at the moment, I'm just doing this stuff visually. I would denote this vector by putting an arrow over whatever letter that vector is being represented by. In a book, it'll typically be in bold. So if this is V and this is W, I wanted to start talking about the arithmetic operations. So that included adding and subtracting two vectors. So visually, what we do when we look at V plus W is put the tail of one vector onto the head of the other. This is usually just referred to by saying, make the vectors go head to tail. So I can pick these vectors up any old and put them down any place I want, as long as I keep the same direction and the same length. So I'll make an attempt to do that, but you know, it'll be a bit antsy. And then my result is going to be drawing the vector from the open tail to the open head. So in this case, the open tail is on V, and this right here would be my vector V plus W. And it's got this direction. It will start at the open tail, but it ends at the open head, and that's the direction. The comment then is that addition is commutative. It doesn't matter the order in which I add. So if instead of placing W onto the head of V, if instead I take V and put it head to tail on W, so let's say, so here is W, and then I'm going to put V in this way. Well, okay, I'm apparently not going to do it there. So let me do it over here. So here is W to the best of my ability, and V would do this. Then what I would do is to draw in a vector. It's going to look like this. Now, I mean, I'm off because I can't exactly draw these vectors, reproduce them. But this would be my vector, V plus W. I maybe could get a little bit better thing if I did this, did it a little bit closer, and then I would get this vector. So this would be my V plus W. Now, these two vectors are the same. The way they're drawn, this is V, this is W. So V plus W appears here as if it's starting at W and ending at V, and it looks just the reverse down here. That's just a quirk of which way you choose to draw it. They're the same vector because they have the same length and they have the same direction. So when you look at a vector, it's not an issue relative to another vector where it begins or ends. It doesn't matter. So in other words, if I have a vector A and this is a vector B, I can pick B up and I can go, here's A, here's B, but I could also go, here's A, here's B. They're the same vector. B is the same. It doesn't matter where it begins in relationship to A. So it's just a quirk of the drawing in terms of where it sort of looks like it's beginning and where it's ending. But it's irrelevant. No difference at all.
Now, when you're adding them together, you still need to put them head to tail, right?
Yeah, when you add the vectors, you put them head to tail. It just doesn't matter which head goes on which tail. You'll get the same answer either way. And you'll see it when we start manipulating with numbers.
Your last drawing is tail to tail.
Yes.
Oh, I'm not adding A plus B here. All I'm saying is that I don't care where you draw B. You can if B should begin here or B is drawn beginning here, it's still B. So he was worrying because, or not worrying, but asking about the fact that V plus W in this order starts at W, whereas down below, V plus W was starting at V. And what I was saying is, I don't really care where this vector has been drawn in. It's irrelevant. The only thing that's important is its length and direction. So I'm not adding these, so I don't, you know, if I were going to go A plus B, I definitely want that and not that. Okay? Okay, so that's visually adding two vectors. If I have a vector like this being A and this being B, what I would like to do is subtract them. And here, like subtraction in general, it's gonna matter whether I go A minus B or B minus A. So let me go A minus B. There are ways to simply set the vectors up tail to tail and then remember where you're supposed to start, where you're supposed to end. I hate that because I can never remember the order. I think the book does exactly what I'm gonna do, and that is switch subtraction over to addition, because it doesn't matter the order when you add. So if this is B, if you'll recall, minus B has the same length, but opposite direction. So I can change A minus B to the addition of these two, and then I can pick up one or both of these vectors, A and minus B, stick them head to tail, and sketch in the resultant vector. So if this is A and this is minus B, and I see already I've erred in where I should place this. Okay, so I've put them to the best of my ability, head to tail, and then this guy right here is my A minus B. So I just play a little arithmetic game with the subtraction to make it look like addition, and then I don't have troubles. Okay? Okay, multiplication involving vectors is different. I'm going to wait on that, because what I want to do now is to come around and mess with how to denote the vectors more analytically. Because if I say, what's the magnitude of this vector, it corresponds to its length, but you probably don't feel like walking around with a ruler all the time. And vectors can be very long, and their lengths can be weird. You know, I mean, it's not easy numbers. So we need an analytic way of writing down a vector. Before I do that, let me remark that you can pick the vector up and move it all over the place And as long as you don't change magnitude or direction, it is the same vector. If I put it so that its tail is at the origin, this vector v is drawn in standard position. That can be either in 2 dimensions or 3 dimensions or, you know, any dimensions. This would be a different vector than what I have here, but the point is A is also drawn in standard position, but it's sitting within a 3-dimensional coordinate system. Okay? So you stick the vector in this position, and I'm gonna just do this initially in 2 dimensions only because I stand a fighting chance of drawing it so that you know what I'm doing. Once a vector is drawn in standard position, its head falls at some point in 2 space or in 3 space. You know, 3-dimensional, 2-dimensional. So let's suppose V falls at the point, well, let me do it here, at the point 3, 2. So if V is in standard position with its head at the point 3, 2, then I denote the vector V by this. Pointy brackets. This is not universal notation. I've frequently seen vectors written with rounded parentheses. And if you see that, it's, you know, by frame of reference, it's context that would tell you if you're looking at a vector or you're looking at an ordered pair. But what you do have is an identification between this vector and this ordered pair. You may also recall that if you're asked to place this imaginary number in the plane, this imaginary number in the plane would correspond to the point 3, 2. And so you have really 3 identifications. You identify this vector with this point, which can be identified with this complex number. Now, we don't need this, I'm just kind of pointing this out. Okay? 3 dimensions goes the same way, except for that you will have 3 slots in here. I refer to 3 and 2 as the components of V. Okay, now, I don't know that you want to try and draw this, but I just want to kind of show you where addition comes from. The point of this is to really get you to see what these components represent. So, if I had this vector, so this is my vector V with components 3 and 2. And if I wanted to add to it this vector, so let me see, -2 and then, so we'll call this vector A, and the vector A would then be written -2, -3. And I want to say what is A plus V, or V plus A. Okay? You can think of this as what happens if water is flowing in this direction down a river or down a pipe, and suddenly it collides with another water flow in this direction, this magnitude. So the way in which we would add these guys would be to place A and V head to tail. And the question is, if I try and draw this in a reasonable way, so I'm going to put V, if I start V here, how far should I go in the X? How far should I go in the Y? In the X direction, I should go 3 units. Okay, so 3 units added onto this -2 puts me over to here. And then in the Y direction, I'm going to go up 2, so I'm going to end up with, oops, somehow I kind of went off. I should end up with this vector. The coordinates of which would be, I believe, 1 and -1. Is that reasonable? If we check this, just very loosely, if this is my V, and I'm going to lift A up and put it up here, and I don't even pretend to have these lengths the same. What would A plus V be? It would be like that. That's my A plus V, and I'm off a little bit because I'm off in these drawings, but you can see I'm getting the same thing. All right? Now, A was equal to -2 minus 3. V is 3, 2. A plus V looked like it should be 1 -1. And you can see that that comes from adding the components. One of the things this does is to really stress that what these components are representing is displacement. Displacement in the x direction, displacement in the y. And this is going to extend over to 3 dimensions. This is how we add vectors when we're given the components. Okay? Now the other thing I can do here is I draw this vector 3, 2. So this is V, which is 3, 2. And I say that the magnitude of V is the length of that arrow. Well, this point right here is the point 3, 2, and this point right here is 0, 0. It's very easy for me, using distance formula, to get the magnitude. It's that length. So what that would be is square root of 3 minus 0 squared plus 2 minus 0 squared. So square root of 13. The magnitude of a vector, if it's in 2 dimensions, let me give the components A, B, is square root of A squared plus B squared. If that vector is in 3 components, the distance formula in 3 components or in 3 dimensions is no different than the distance formula in 2. Square root of A squared plus B squared plus C squared. Magnitude of a vector is denoted by writing this. Double lines around the vector symbol. This is also not universal. You will also see single lines. Our book uses double lines. Different books or papers or people will write it, I don't know, just accordingly. Either way, it's going to look either like the double lines or like an absolute value. An absolute value is also just a length. You know, if you take a look, absolute value of -3 is the length between 0 and -3. So, you know, that's where this is coming from, but I think to keep people from getting the 2 of them confused, some people just will use this. Either symbol works for magnitude. Okay? Something else I was going to say. Now, wait a minute. What was it? Magnitude of V. Dang it. I cannot remember. Oh, that's what it is. Okay. If I have a vector, call it V, And I tell you, it starts at the point 3, 1, negative 4, and it ends at the point 2, negative 3, negative 10. So, I'm giving you a place where it begins and a place where it ends. If I want to write that vector in component form, well, again, think about the components of a vector as being displacement. I'm not going to literally draw these 2 points. It's 3 dimensions. It's a pain to try and draw. But the displacement, when I start at 3 and I move up to 2 or down to 2, the displacement is negative 1. So the vector v, I would get its components by going, here's the ending point, so going 2 minus 3, minus 3, minus 1, and then minus 10, minus a negative 4. Make sure you begin at the place where the vector ends. So v here would be negative 1, negative 4, negative 6. And this is in keeping with the notion that the vector is recording displacement. Okay, any questions here? Okay. Here's a vector. Its magnitude, which I would denote with these double bars around A, square root of the x component squared plus the y component squared. So that's 1/2 plus 1/2 adds up to 1. Square root of 1 is 1. A is what we call a unit vector. Its length is 1. There are going to be various times in here where I need a vector that is maintaining the same direction, but I need it shrunk down to length 1. So you will see problems such as the following. W is a vector 1, negative 2, 3. Find a vector